We now want to consider the whole business of setting up rate laws that tell us something about the kinetics of a chemical reaction, that is, how fast it will occur. Now, I want to return to this sort of hypothetical reaction that we set up in the previous module to talk about chemical reactions, just as a starting place. We're actually going to go to something that looks even simpler than this before too long. And I'll remind you that N sub alpha, where alpha can be A, B, C, or D, just represents the number of moles of that substance. So if we're considering a change, that is a change in the extent of a reaction, we want to use that extent of reaction parameter somehow to help us track that change. So remember that we wrote down an expression, for example, for component A. It might look something like this, where the number of moles of A is just going to equal its initial amount plus a change that is proportional to its stoichiometric coefficient. And then I would multiply that by the extent of the reaction. Now, what I want to do in this case, we didn't worry about how that extent of reaction changed in particular. What I want to do, though, is consider it implicitly to be a function of time. That is to say, the amount we start with is not going to change, or it could change from one experiment to another, but it's not going to change during the reaction. And the stoichiometric coefficient certainly isn't going to change, so the time dependence in the number of moles of a component like A is going to be tied up in this extent of reaction parameter. So now, if I write down the change in the number of moles, okay, this part doesn't change, so it's all going to be over here. So it's going to end up being something like the stoichiometric parameter times the change in this extent of reaction parameter. But now, if this depends only explicitly on T, then that should be an equal sign. Then I can similarly write that this is just going to be dc dt times dt. So we capture all of the time dependence here. Now, I'm going to be more specific than this and say that I really care about this because this is how we're going to specify the rate of reaction. So I want to isolate this derivative of C with respect to T because that's telling me how fast that extent of reaction is changing. So it'll be equal to 1 over the stoichiometric coefficient times this number of moles of A that are changing. Now there's a couple of things that I want to do that also is a little different from the previous module. I had been writing this so that we would understand that the stoichiometric coefficient was negative if it was a reactant and positive if it was a product. I want to be more explicit than that, and I'm going to now put a negative sign in front of this so that we can track that. The other thing I'm going to do is I'm going to implicitly divide by the volume. Now, why would I do that? We don't normally keep track of the number of moles of a substance unless we're repeatedly weighing a chemical species, but we can keep track of its concentration. So by dividing by volume, I can now convert this quantity into a change in the concentration of A. So that means that I can effectively write that this derivative, dt, is going to be equal to minus 1 over the stoichiometric coefficient of A times this derivative. And I'm going to also specify that this is a derivative with respect to time because I had dt over on this side of the equation, so now I'm basically dividing both sides by that. All right, so when I write this way, it's a little bit more suggestive. I'll remind you, though, that we could do this for each of the components of this reaction. So, in fact, this is also going to be equal to minus 1 over VB times the time derivative of the concentration of B. On the product side, I could also write this as 1 over nu VC times the derivative of C with respect to time, and D. All right, so which one of these do we choose? It actually doesn't really matter that much. I will tell you that conventionally we tend to focus on the reactants when we talk about reaction rates. So we're going to really focus on these two ways of writing reaction rate. And most of what we have to say this lesson, I'm going to just be focusing on one of these. But all of these are equivalent ways of writing down the rate of a reaction. And they're equivalent because by defining the reaction rate in terms of the extent of reaction parameter, we can make them all be equivalent to one another. So this is, I guess, a little bit of the background that I wanted to lay out here. So this extent of reaction parameter is derivative with respect to time. We're going to relate to the rate of the reaction. It's basically telling us how fast the reaction is going to occur. Now, if I write something out for the rate, I want you to be thinking in terms of it is the rate of disappearance of a reactant like A or B. Okay, so this will be our understanding when we write the word rate on one side of an equation, is that we're really talking about a time derivative of the concentration of one of the species in the reaction. Now, this alone doesn't tell us anything about the rate of the reaction. It's simply we're writing down mathematical definitions, if you will. If we really want to understand a reaction, though, we would have to relate this to something else. And it turns out that, helpfully, nature has basically shown us that this rate of reaction is often proportional to the concentrations of the reactants in a mixture. So in other words, I can relate it to these concentrations if I'm talking about a reaction like the one up here. All right. Now, it's not exactly equal to that. We need a proportionality constant. And it turns out that these two concentrations are also raised to different powers. They could be the same, but they're often different. Okay, so these two exponents, if you will, are telling us something about the order of the reaction in each of these different reaction species. And in fact, we're going to define something like the total order of a reaction is going to be their sum. So I'll often be referring to the overall order of a reaction, and what I mean by that is the sum of the exponents that appears in this expression that relates the rate to the concentrations of the reaction species. Now, this particular thing is something that we would call a rate law. Okay, it's relating the speed of a reactant changing its concentration to the concentrations of not only that reactant, but all reactants that happen to be together there. Now, you may ask, why am I focusing on reactants? Well, at the beginning of a reaction, that's all we have typically is the reactants that are combining. Now, we could start with different mixtures, and we can talk about that, but let's just say that theoretically, the reactants are the things that we start with, and they evolve through a chemical change, through a chemical reaction to generate other species, which we'll call products. All right, this thing that I've put in here, this proportionality constant, is something we call the rate constant. And we saw in the earlier module, in the previous module, that we could relate this rate constant in a very heuristic sense to a whole bunch of other constants that themselves were functions of temperature. And in general, we'll find that these rate constants are dependent on temperature, and we'll quantify that a little better probably in the next lesson. Okay, so when we're done with all of this, we're going to end up with a rate law that looks something like this. A rate that's equal to K times the concentration of A raised to some power times the concentration B raised to some other power. Now, I want to be sure to clarify that these powers here are not the same as the reaction coefficients. So they could be equal to them, but they do not necessarily have to be equal to them. They're not directly related. So don't fall into the trap of saying, oh, well, I've got these integers up here in the balanced chemical equation. I can just put those in to create my rate law. That is not the case. In fact, it turns out that in order to find these the values of these exponents, we actually have to do some experiments and do some analysis of the data to determine what those exponents are. So we can think of this rate law as a phenomenological rate law. It is simply describing for us the general behavior of the rate as a function of these concentrations. Now, the one last thing I want to talk about a little bit is units. And units, of course, has been our pet bugaboo all semester long. But in this case, what I want to pay attention to is the units of rate, first of all. Well, rate is related to a derivative of a concentration with respect to time. These stoichiometric coefficients are just number holders, so there's no dimension there. So the rate is going to have units of molarity per second. All right, and that's going to generally be true of any reaction that we talk about. Now we relate the rate in this expression to molarity raised to a power and another molarity raised to a power. So in fact, we're going to have that rate is equal to K times molarity to the m sub a times molarity to the m sub b, and you'll notice that this just gives us molarity, K times molarity raised to the ma plus mb, but we've defined that to be the total order. So m total order of the reaction. Now, what does that mean? Well, that means that we have to set the units of our rate constant so that it ends up generating the correct units for the rate. So what does that mean? That means I'm going to have molar per second. On one side, I'm going to have K, and then I'm going to have molarity raised to the total order power. So when I divide both sides by this quantity in units, I would find that our rate constant is going to have units of 1 over the molarity raised to 1 less than the total order times seconds. All right, so this is a relationship that you'll want to remember. It depends upon the order of the reaction. So rate constants for two different reactions may have different sets of units because they have to have the units that make it work out so that the rate itself is molarity per second.